Hello, everybody. Welcome to this to the latest session of the Nodes 2019 conference. So this track is graph algorithms for community detection and recommendations. It's the next in the series of talks about the Neo4j graph algorithms library. So if that's not what you're expecting, you probably need to find your way to another track. So we've got two presenters for this talk. So my name is Mark. In case you've never met me before, I don't normally have that cape, but I work with Michael Hunger in the Neo4j Labs team. So Michael talked about Neo4j Labs in the keynote at the beginning of the day. So it's a team that helps get Neo4j integrated in sort of different technologies, and we sort of explore different areas where we think people might be interested in applying graphs. And so this talk is one of them. So I guess now I'll let my colleague, Amy, introduce herself.
Hi, everybody. My name is Amy. I work on the analytics and AI programs. I do like Peeps, and if you don't know what Peeps are, they're a marshmallowy sugar candy shaped in the form of little chicks. And I like to make dioramas of them, so you can Google that to see what those are about. But it's actually quite a bit of fun. In this webinar, we're not going to be talking about Peeps, but if you go to the next slide, Mark, we will talk about graph algorithms for community detection and recommendations. We're going to be looking at Twitter in particular and looking at that social graph, looking for influencers, and also identifying communities. So one of the first questions that we usually get is, what the heck are these, algorithms and graph analytics, and why would we want to use them? In the next slide, we just do a quick comparison. You can see there's queries and there are graph algorithms. Queries we're all probably pretty familiar with. You've got something specific, very specific, that you're trying to look for, trying to match a pattern. Usually what you're looking for and you're trying to make a local decision. It could be something like how many people 4 hops out from this person have a similar or the same phone number, or have some marker on their profile. On graph algorithms, we're usually looking at something more global. So doing some kind of analysis, there's often an iterative approach, and you're learning based on the overall structure and the topology of the network yourself. So the other question is, okay, so when don't I need a graph algorithms? Like, is it good for everything? Well, it's not good for everything, good for a lot of things. But if you have questions with just a few connections, it's kind of flat. Like, I just want to go, one connection out and understand something. I really know exactly what I'm looking for. It's very specific. Maybe I just want to know the average height of people in the US, or I want to know an average, kind of ratio. So basic statistics. And a good example of that when you wouldn't use graph algorithms is maybe you do some regular reporting, such as sales summary reporting. It's very defined and it's well organized. So to get back to why do you actually need graph algorithms, there are 3 things that people generally do with graph algorithms. And they have to do with trying to understand and predict more complex behavior. And one of the first things that you can think about that's easy to kind of visualize is, how do things spread through a network? Maybe you're talking about a rumor, maybe you're talking about a disease, but we want to understand what paths do these things take. The other thing you would be thinking about is something about maybe how things move, but it's more about flow. Like, what's the capacity in my network? How much traffic, how much telco traffic can I route on my network? What are the dynamics if one area goes down? If I have a router that goes down, what's the secondary paths that we might take? And the third area that people generally look at is understanding the dynamics of groups. And so that could be interactions between different groups and between different communities. It could be things about resiliency. Is my group likely to stick together? Are they likely to fall apart? And all of these things, what's in common with these is that you're really trying to understand relationships and structures. And so using graph algorithms, like, how do I actually employ them? There are 2 big ways, Mark, if you go to the next slide, thank you. There are two kind of major areas. One is just to understand, to do the analysis itself. So I'm trying to explore my graph. I want to find patterns. I'm looking for some kind of structure. I want to find these measures. And you can set a threshold to any of these measures and then make like a general assumption or prediction. The other way that's becoming really popular right now, a lot of people are using graphs and machine learning together. And in this case, they usually start with those same graph algorithms or a set of those graph algorithms. They run them, you come up with a metric, and then you do an extraction of that metric into a table or into some kind of vector that you can then run machine learning on it. So those are the ways that people usually deploy them. And the Neo4j graph algorithm library, we've got quite a few algorithms. If you guys haven't read the graph algorithms book yet, it's a great way to get started on it. You can get a free download from Neo4j. We've got over 45 graph algorithms. I keep updating that number because every time I turn around, somebody like Mark or others on the team have added more. But they generally fall into 5 categories. Pathfinding, so how do you find the optimal route or evaluate the quality of a routes that you have? Centrality, which is about finding the important nodes and the influential nodes in your network. Community detection, and maybe we should really call this community understanding, to tell you a little bit about what the clusters and partitions, but also a little bit of the quality of them. Are they tightly knit? Am I looking for hierarchical searches? Link prediction is an interesting category that is a little more focused on nodes themselves, and it looks at whether nodes are likely to become connected in the future, or there's a connection that we just don't have in our data, that they should be connected, we're just not seeing it. And that's based on how far or the topology of the nodes between each other. Similarity, again, looking at how alike nodes are based on different factors, whether it's attributes of the nodes or the relationships that they have. So a quick look at a list of them, and I realize that I'm actually missing quite a few on this. Just to show you, we do have quite a few algorithms. You can always go to the Neo4j docs to look at the latest and read the details about those algorithms. So if we want to look at how do you actually use these, how do you call these? You can call the graph algorithms after you have the library installed. You can call them as a Cypher procedure, just like you would any other Cypher procedure, and then pass in whatever configurations and attributes you might have, what labels do I want to use, what are the parameters that I want to set. And then you have a choice of whether you want to stream the results or write them back to the graph. If you do decide to stream them, just realize that you could have a lot of results to look through. So so Cypher projections, this is a really powerful way of working with graphs and algorithms. It basically lets you pass through a Cypher statement to match specific nodes and relationships and get the graph in the shape you need. So for example, if you needed to look at a subset, you want to run an algorithm on a subset of maybe a certain people with a certain zip code, that you want to do your relationship, kind of investigate your relationship and use your algorithms on those. You wouldn't necessarily want to run that on the whole graph. This allows us to kind of break that down. It also allows us to do a couple other really neat things, and I think the next couple slides show us an example of using Cypher projections to infer some interesting results as well. So the team, actually the DevRel team actually did, and the labs team did a really nice example. Will Lyon was really involved in looking at Russian Twitter trolls. And so in this example, we were looking at tweets, where they came from, who did them, and who retweeted them. And what we were able to do with we were able to infer relationships using the Cypher projections for the graph. And so you can see here we've got a couple of users on Twitter, and we've got a tweet that was posted and then retweeted by somebody else. And what we're able to do there is actually infer, and I think the next slide shows the inferred relationship. Great. So we're able to actually infer that there is a relationship between the first Twitter user and the second Twitter user, even though it's not direct. And so you can use cipher projections to infer relationships. And you can also then run the different algorithms on them.
Yeah, and so on this slide, we're seeing how you could run the PageRank algorithm over that Twitter trolls graph, where the relationships or the inferred relationships that Amy mentioned that we are defining in this second query here are implying that troll 2 is amplifying troll 1. And so the idea is if you have a relationship pointing from you to somebody else, it means you're amplifying. You're saying, hey, this person is credible. I think their stuff is good. And so that's what we're using the retweeted relationship to mean here. In the example that we're going to look at in this talk, we're actually using a more direct amplification, which is that if somebody follows the other person, then it means that they amplify it. But you could even imagine combining both of them and saying, well, follow is like, it's kind of a weak amplification, but maybe retweeting, maybe liking something is a little bit more of an amplification, and maybe retweeting is the best amplification. So you can actually do levels of amplification if you wanted to. So if we go to the next slide, just to give you a quick breakdown of how this works, because it's not quite the same as what you'll be familiar with from that querying approach that Amy described right at the beginning of the talk. So normally when you're writing queries against Neo4j, you write your query, it sort of like gets compiled by the Cypher engine, it runs it against Neo4j, it maybe loads some stuff into memory while it's running, and then it sends it back. But the model here is actually a little bit different. So the way it works is we run our, there are kind of two ways that you can do it. But generally, the first step is it has this graph loading process, which loads our projected graph, where the projected graph could be the whole graph. If we passed in null and null for the label and the relationship type, it would just load everything into memory. Or it could be, as Amy pointed out, it could be a subset of that graph, which could be defined by using a node label and a particular relationship type, or with a cipher, set two pairs with the pairs of cipher queries. And it loads this into memory, and we can either choose to keep it there, or we can choose to run it in a mode where it's actually just going to keep it there for the duration of the query, and then it'll be gone once the query is finished. And so then, as you can see, the third step is run the algorithm against that in-memory projected graph. And then again, as Amy pointed out, either those results will be stored in Neo4j, or they'll be streamed back to the procedure again. So those are the steps, and pretty much all the procedures are following this more or less. So we're a colleague of ours called Irfan, who presented a bit earlier on about graph visualization. So he was used to be working on the Neo4j Bloom team. He started off this project called Neuless. It stands for Neo4j Euler. So Euler being the creator of graph theory way back when. And he created this graph app, which is a React application that sits on top of the graph algorithms library and allows you to use graph algorithms without having to write any of that cipher code that we just looked at on the previous slide. So this is a really good way of getting yourself started. So we consider this as like a training wheels for doing graph algorithms. If you want to install it yourself, you can get it from here. So if you go install.graphapp.io, this is the graph apps gallery where you can do one-click install of different graph apps that have been either written or curated by the Neo4j Labs team. And so you can see here on the first row, the third item is the Neo4j Graph Algorithms Playground. So I'm just going to quickly show you what it looks like. So this is the Neo4j desktop. So if I just go out, so I've got my Twitter project over here. So this is the Neo4j desktop. You can see my list of projects is as unorganized as my downloads folder. But I found our Twitter project. I've got a graph running here, and then I can choose to add application, and I've chosen to add the Graph Algorithms Playground. And if I then click on that, I'll get this UI. And so you can see I can choose my type of algorithm down the left-hand side. So it could be a centrality algorithm, I could run a community detection algorithm, a pathfinding algorithm, or a similarity algorithm. And then along the top, I get the different ones that I can run. And so, for example, in here, we could then choose to say, hey, I want to run this degree centrality algorithm on the user label follows relationship, and I can run that, and it'll show up in here. It'll run against the database that I have it running against. But we're just going to go back to the slide so we can briefly explain what this data set is before we start playing with it any further. So what we're going to do is we've actually created a graph of the Neo4j social graphs. It's a little bit meta. So we scraped the tweets from the last 9 months of the Neo4j and graph database hashtags. So we actually got all the tweets, and then we looked at the users who had tweeted those, and we got their follower and friends graphs. And mostly we haven't pulled in the retweets like Will and David did on the Twitter troll. So we're just going to focus on the followers graph for this talk. So we're going to look at those follows relationships, and we're going to see what we can discover about this graph community. We're using a tool called Twint. So the official Twitter API has quite strict rate limiting, and mostly they don't want you to extract that followers graph, but it's really interesting for doing graph analytics. So we're going to use this scraping tool to allow us to get the data, and then we're going to use it. We're going to use Noila to then explore it. If you can't be bothered with the scraping step, we've actually created it as a sample graph in Noila. So if I just quickly go back to the Noila project again, see the little yellow little sample graphs icon. If you click on there, we've got several data sets that you can use. So we're going to use this Twitter one that I curated, but there are two other ones, one by our colleague Lasse, which contains European roads and the links between them, and then another one over here, which is called the which contains interactions from the Game of Thrones television series, and this was curated by Andrew Beveridge, and he's actually done a lot more work than I have on the Twitter one, because he's taken the raw text of the scripts from Game of Thrones, and then he's worked out what interactions happen between characters based on how closely they appear in conversations that happen in the dialogue in Game of Thrones. So any of these are really interesting for quickly doing graph analytics type work on. But if we come back here, I'm going to hand back to Amy, and she's going to talk us through what type of analysis that we can do. And then once we've done that, I'm going to quickly show how we would do that using the Noila tool.
Cool. So let's just go right to the next slide. We kind of look at some of the different types of centrality. So these are just kind of 4 of the main types of centrality people typically look at, and we're gonna look at 3 of the 4 of these in a little more detail. They're kind of nuanced in how they interpret what influence means. So degree is looking at how, what are the number of connections somebody has, and you can see in the upper left that the A has a high degree, has a lot of connections. Closeness is looking at how quickly can a node actually reach other nodes and all of the other nodes. Betweenness is your classic bridge, like what has a lot of influence over not just reaching other groups, but you can also think of betweenness as, or any of these really, as influence on an overflow of resources, flow of information, potential bottlenecks in the case of betweenness. And PageRank, of course, looking at the classic overall influence, not necessarily based on number of connections. So I think first we're going to look at degree centrality. And let's just go to the next one. Great. And as I said, it measures the number of direct relationships. And this is looking at degree in degrees. So, if you can see by the numbers, somebody with no relationships going into them is a 0, and you can see 6 there has 6 relationships coming into them. This is probably the simplest of the centrality algorithms. You can look at in degree if you want to look at popularity, out degree if you're looking at gregariousness, but you can also globally average this to take a look at what your like how connected your overall graph is. Just realize that you've got some super nodes in there, or you have some lumpy distributions of relationships that will skew your overall results. And it's probably other algorithms are probably better for influence over more than just direct neighbors, but this will give you direct neighbors. Now, when would you use this? So next slide, we look at an example looking at the likelihood of somebody having a flu, and that's for an individual probability. Like if I have a lot of friends, possibly I'm more likely to get a flu if those people within my network also have the flu. So you can understand a lot about immediate and very fast type of connections, and just as I said, you can do a quick estimation of your network to look at like min, max, mean degrees, and things like that. So the next algorithm.
With this one, like people who are not really into graphs, this is kind of like the one that they would use, right? Where when people talk about Twitter analysis, they kind of look, oh, it's just the person who has the most followers. They must be the most influential person, and they point out like people on Twitter who have the most followers, and it's like, okay, that person has the most influence over stuff that's happening. But we'll see from the next algorithms that there could be people who have less direct followers, but maybe more influence in slightly different ways. So the next one we're going to look. I guess this is an example of running it. So I guess we did this one when we were in Neulerland. And you can see here, like it's probably not that surprising. You can see the Neo4j accounts top, TechCrunch is second, AWS is third, and this is not pulling in all of their followers. It's just the followers who have done something to do with graph databases. We see we've got Michael Hunger and Emil are the first people accounts that we see in there. And then Kirk Bourne, who wrote the foreword for the Graph Algorithms book that Amy referenced before as well, is in the top 10. Cool. So if I go to the next one.
Hey. PageRank, yeah. So let's look at PageRank. So as Mark was saying, degree is something that a lot of people will say, well, they've got a lot of friends or they have a lot of followers, so they must be really important and have a lot of influence. But what we can say, and that's a very direct measure. PageRank, though, probably one of the most popular algorithms, shows how you're actually looking at influence of nodes in consideration of their neighbors, how many connections, and the importance and the influence each one of those neighbors have. So it is a little iterative. It's kind of a meta thought of influence. But with PageRank, the idea, if you think of it as something like the influence of let's say a foot soldier that has a lot of friends is not going to be high as a foot soldier at the same rank that happens to be friends with the general. So your friends and their influence and their ranking are going to impact how influential that node is. So that kind of shows you what kind of this indirect and overall influence over the total network. The one tip, I guess, on this one is there's dampening factors that can be set that change how quickly you jump to other nodes, so you don't end up in in a dead end. And you just need to look at that and change that. The defaults are set for a power law distribution, so a very kind of a situation where you have hubs and spokes, and if your data doesn't distribute that way, you just want to take a look at that and play around with different dampening factors. And the other thing with PageRank is just be very careful about mixing node types, because PageRank assumes, at least the way most people implement PageRank, it assumes a single node type, and so looking at the influence of a human and a restaurant doesn't really make as much sense, because you're ranking people against businesses.
Yeah, and I guess also to keep in mind is the relationship type implies that you are kind of giving some credibility or amplifying the node that you're pointing to. So if you just have a relationship that doesn't mean that, you get a fairly nonsensical result from running this algorithm. Should we go to the next one?
Yeah, let's look at when you'd use it. So again, looking at kind of the broad influence, and I think Mark brings up a really good point that the relationship actually indicates there is some kind of influence or amplification there. There are a lot of domain-specific variants of PageRank. So there's personalized PageRank, which means that every time you hop, you kind of go back to either a particular node or a set of nodes. That's used actually in some very interesting ways, such as making recommendations, like personalized recommendations. This example here with the fraud detection in the feature engineering where PageRank was used was actually using personalized PageRank as well, so that when they looked at the influence of and interactions between pharmacies and doctors, they actually went to be personalized about it, to be personalized to the domain of the doctor. So looking at an ophthalmologist differently than an oncologist and what they prescribed. Also just your classic, as you can imagine, who to follow. So Twitter uses a PageRank and a personalized PageRank actually to recommend who to follow.
Okay, so let's have a quick look. How does that look on our graph? So pretty Neo4j and TechCrunch have switched around. I think there. So TechCrunch has a higher transitive influence. You start to see there's some people that have pushed up the rankings. So Michael Hunger has pushed up, and Hillary Mason is now quite high up there as well. So that kind of tells us that although maybe they don't have the most direct followers just on their own, that they are followed by other influential people. So that's effectively what that's telling us. Although here it still is obviously dominated by those three company accounts, I guess. Which leads us to one. So go on.
Oh, I was just going to say, in the PageRank, the other thing to think about is you're always ranking. I mean, it's a rank, so the actual score isn't as meaningful as what's on top, what's second, what's fourth, what's 10th itself. So a lot of times I'll look at this by just the, what's first, second, third, the actual rank, and I don't bother looking at the actual numbers.
Yeah.
So.
And now for one slightly different one. Is betweenus centrality.
So centrality is betweenness is a lot of fun, just because of the fun concept, and it's basically it's a measure of the sum of percentages of shortest paths through a node. Okay, kind of a mathy way to think about that, but as you can see by the A node here in the middle, that's got the highest betweenness centrality. Betweenness centrality is really a look at bridges between communities, and and it makes sense. You're a bridge between communities if the number of shortest paths of potential shortest paths go through you, and it can be a very computationally heavy algorithm if you're running it kind of in its original form, because you have to look at every path, and then understand the shortest paths, and then do some calculation on that. So we and others have some approximations. Our RA-Brands approximation, you definitely want to use in large graphs. You may also want to pare down, so you're not looking at between the centrality of everything. Maybe it's just of your products, maybe if it's of the components in your products, maybe it's of the people in your network, or how you're routing packets in an IT network. It does assume, betweenness centrality does, that the communications happen between nodes along shortest paths, so it gives you more of the potential for the bridge, not necessarily it in actual real life. So that's just something to think about, is my communications and my routing actually going along the shortest paths as I would hope it to be efficient. So let's look at a couple use cases with betweenness centrality, which are kind of fun. As you can tell, identify bridges, control points as well. So bottlenecks, vulnerabilities, control points. This example here was an evaluation done with an electric grid, where there was a country, you can probably guess by the picture which one, but looking at rippling and cascading failures they were having in their electrical grid, and they thought that if they just added more redundancy, that the cascading failures and the resilient would go down and the resiliency would go up. But when they looked at it as a graph and they looked at where the vulnerabilities were, they found that if they actually removed some of the control points or removed some of the communications between the grid, that their resiliency actually went up. And the reason why is, if you can imagine failure spreading like a disease or a communication, they were actually providing too many routes for those failures to propagate widely. So that's a fun one, and I think the next slide we have a couple pictures of a picture of that in Noilor itself.
Yeah, so this is Noilor running between a centrality, and now you can see this starts to be quite different than the previous two. So degree and PageRank were more or less showing us the same people, but between a centrality starts to show us, as Amy said, it's like the local node. So it's people who are connecting like mini communities inside the bigger Neo4j community. And so you can see in position number 3 is our colleague Will Lyon, and so he's really big into GraphQL. And so he'll be the bridge connecting all those people who are really interested in the GraphQL world and have come into Neo4j land via the Grand Stack. So they'll be connected to him, but they maybe don't really know anyone else in the Neo4j community. So Will's like the glue node sitting in there, and you can see there's also the GraphQL weekly node, maybe doing a similar job. There's the lucasoft.co.uk, so it's a PHP. They do a bunch of PHP stuff, and so there's a PHP community. They'll be connecting them in. And you can see maybe Arcade Analytics. It could be like a BI Analytics tool that was probably connecting to a bunch of other people. And I think that one has an integration with Neo4j. And so presumably any people that are interested in graphs that are but are interested in it via Arcade Analytics would only be connected to the rest of the Neo4j community via that account. So let me just quickly show you how you would go about it. So if you were to run those, in this case, we're doing these centrality algorithms here. So we might choose, okay, let's do the betweenness one. So we might select our label, select the follows relationship. We can choose to store the result on a property, or we can choose to just stream it back. So if we run that one, we should see the same result as we had before. As you can see, we've got Will in position 3. We can also do a chart view. So this one's not quite perfect. It's still chopping off the names a little bit, but this one kind of gives you, this sort of shows that actually the Neo4j account is still massively influential in this respect. And the others are much lower scores. And you can't really see that just from the what do you call it, like the scalar values on a table. And we can then go through the previous results we've run. So that's the degree centrality one. Can do the same for PageRank. We can also do it for centralities. So we could run the different centrality algorithms. We've got a few to choose from here. But before we, the view that we do of the centrality algorithms is not quite as is not quite so easy to decipher. So we're gonna go back to the slides to explore the communities within the Neo4j community. So community detection algorithms help us to evaluate how a group is clustered or partitioned. And so the next thing that we're interested in is, well, we know that Will is a local bridge, and we know that Lucasoft node is a local bridge, but we don't really know, like, what are they a local bridge to? We could, I guessed what I think it is, but we can explore it and see whether or not a graph analytics approach can actually tell us. And so we're going to use an algorithm called the Louvain modularity algorithm. And so this one is one of the many modularity algorithms, but again, it's not doing brute force modularity computation. It's more of an approximation approach. And the idea is it's trying to put nodes into communities, and then it scores the community based on how closely connected nodes are within the community versus how well they are connected outside. And so you're trying to find almost like the ratio between those two things, and you want to have nodes in a community are more tightly connected inside than they are to outside. And you'll never get a perfect result, but this one is trying to find an approximation, and it's an iterative algorithm. So on every iteration, it's sort of testing, can I move this node out of that community into another one, and does that make things worse or better? And so you'll get to a point where you're like, okay, this is reasonably stable, and I think I'll probably leave it there, and that might be the communities that you end up with. One cool feature of this is that on every iteration, you can get it to tell me what the community looked like after every iteration, which allows you to see what we call intermediate communities. And so after one iteration, you might see like a few smaller communities, but as the iterations go by, they might end up being merged into larger ones. And so if you want to know, so at the end, you might end up with just 10 communities, but if you want to know what's the breakdown of those smaller ones inside the 10, then you want to go and look back at those intermediate communities that were computed along the way. And as it says on the slide here, you can do this by using relationship weights as well. So if we just have a quick look at the use cases of this one. So as we can use it to find communities in large networks. We can also use it to evaluate different grouping thresholds, and we can also try and find hierarchical structures in data. I guess, Amy, do you have anything else to add for the fraud ring stuff on the right?
Yeah, so one of the interesting things on looking at frauds and actually any kind of a network with Louvain is that you also have the ability to define, because you get the intermediary categories or groups, you have the ability to define how tightly you want that community to be defined, and so you can actually kind of set kind of a threshold to say, is this somebody who's just not behaving well, or is this a really, perhaps a really tight community that we need to look at as a potential fraud ring?
And so we actually now reminds me that we're in the Kafka presentation, so showing how to build a Kafka pipeline. We have an example in there showing how you would use the Louvain algorithm to detect fraud rings, and then in that case, then feed those potential fraudulent people into a Kafka stream for future analysis. But that uses the Louvain algorithm to do it. So if we just have a look, if we run the if we run the Louvain algorithm already and had it stored, this is how we would find the top 10 nodes group, but for each community. So we're showing the top nodes based on PageRank and what community they fit in. And if we run it in the Neo4j browser, this is what it looks like. So we end up with a bunch of different communities. So we've named them with little logos on the left-hand side. So that the algorithm itself just gives you a number, and then you sort of carry on from there. So you can see there's a couple of data science communities. We can see like big names in the data science world: so Hilary Mason, Kirk Bourne, Ben Lorica. We can see the Cloudera account in there. Then if we go down to the second one, we can see data science Rene. We've got our bloggers. We've got a couple of other data science people. The big Neo4j cluster is in position 2 on this diagram, so we can see that the Neo4j accounts in there. We've got Jim Weber, we've got Michael Hunger, we've got Emil. The third row is probably, it's hard to completely categorize that one, so we haven't attempted it, but you got AWS, you got Madasai, who works for AWS. Some of the others are they're not necessarily AWS employees, so we weren't entirely sure that that's necessarily an AWS cluster. But if we come down a bit, you can see there's a bit of a Spring cluster with Josh Long and Rod Johnson and Mark Heckler, who's a Spring advocate. Spring Central accounts in there as well. And then if we go down to Community 6, that's a semantic web cluster. So what would we do with this? So the second part of this talk was, the second part of the title of this talk was, well, how would we make recommendations by using these algorithms? So I'm gonna let Amy wrap up by teaching us how we might do that.
Yeah, so if you're trying to, let's say you want to do recommendations, or you have a distribution or an offer you want to make to particular people, there's a couple different ways you could do that. The first algorithm we talked about which was degree centrality on the far left here. You might use this if you want to get a message immediately in front of the most people in that community, or connected to, in this case, Neo4j. So, hey, I need to get a message out immediately to the Neo4j community. I want to use and target the Neo4j Twitter account. The second one is looking at overall influence, and PageRank was this example. So in this case, I'm looking at the influencer with the broadest reach to the biggest amount of people, and maybe something that takes a little longer to propagate. We want that ripple effect, and it's not as maybe time critical. And in this case, as Mark said, that was the TechCrunch had the highest PageRank. And then the third example here looks at communities, and this is when we have different promotions and tweets and offers to different sub-communities. So maybe the Spring community versus the Microsoft community versus the data science community. I want to use different words. I want to offer them different things, and I would use that to target. And then the fourth one, which is really interesting as well, is using those bridges, looking at that between the centrality. I want to find a person who's got a lot of influence, but can help me get my information or my offer or my target to the specific sub-community I'm interested in. And in this case, it was Will Lyon with as the bridge between Neo4j and GraphQL.
Cool. And so to wrap up, we've got a few resources for you. So Amy, Will, and I have built a couple of online training courses. So with slightly different focuses. So we've got the first one is it's all about applied graph algorithms. So in this one, you take you're kind of building a web application while using graph algorithms to enhance the application and kind of make better recommendations or better suggestions to the users on things to do. And that's all based on a Yelp data set. And then the data science with Neo4j one, we're kind of approaching, if you remember at the beginning, Amy talked about two uses for graph algorithms. We've got, you can use them directly, or you can use them as part of a data science or machine learning workflow. And this second one looks at more how we would do that. So it kind of takes us on some of the steps of how you might do graph data science. So we start by exploring a data set. We might then make recommendations by using some graph algorithms, and then we move on to making predictions by using graph algorithms as part of a bigger machine learning pipeline. So if you're interested in learning more about how to do these in a bit of a hands-on way, I'd encourage you to take a look at these online training courses. Of course, it would be remiss of us to do a talk without mentioning that we wrote a book on this topic. So this is available for free on the Neo4j website. So you can see there, neo4j.com/graph-algorithms-book. So if this is intriguing to you, don't forget to take a look at that. And finally, for our last 5 minutes or so, we're going to leave this slide up, and we'll let Jennifer ask us some questions. But these are the questions that you need to answer rather than that we need to answer. And the answers for all of these were somewhere in the presentation. And so you got to use these if you're participating in the Hunger Games that Karine announced during the keynote. So we've got 3 questions. So the easy one is, which of these algorithms is a community detection algorithm? Slightly harder, what is not a good use for a graph projection? So that's a cipher graph projection that we talked about when we were talking about how you execute algorithms. And finally, a bit of a tricky one. So you got to have been paying attention when Amy was explaining this. So Amy pointed out that the default dampening factor for the PageRank algorithm is 0.85. But what distribution of relationships does that work best on? So those are the 3 questions. r.neo4j.com/hunger-games. You'll need to select in the drop-down graph algorithms for community detection and recommendations. And then if you fill in your letters for each of those questions, then you can participate in that competition. Otherwise, I guess we can hand back to Jennifer because I cannot see the questions.
Okay, yes. So we have several in here. The first one is, are you loading the graph via the Cypher loader? Could you paste an example of your queries?
So yeah, I guess we could. Yeah, so in the ones we did in the Neuler, we were not. So you can have a look here. What query actually gets run? So you see on the screen here. So you can actually go and generate yourself a Neo4j browser guide if you want, which will exercise the query. So in the one here, it's loading an in-memory graph of $label, so parameter label, which in this case is user. Relationship type follows. So it builds us an in-memory graph which contains nodes that have the label user, relationships that have the type follows, and it's just an in-memory structure containing basically arrays. So it's an in-memory array structure, which in this example it lasts for the duration of the PageRank query, and then it gets torn down afterwards. There is a separate thing that you can use called graph loading. I'll just quickly show you. So if we just search for Neo4j graph algorithms, so we go in here. There's a whole section on the projected graph model, and if you have a look at named graphs, we show how you can load what we call a named graph. So you can actually say, hey, I want to load my graph with a particular label, a particular relationship type, and I want you to keep it around. So this one will keep it around in memory, and then you can choose to then process it at a future stage. I don't know if we have an example of that in here. Let's have a look. PageRank. Yeah. So if we wanted to then use it, we could say, hey, call me algo.pagerank. You'd set in a null property, a null value for the node label and relationship type, and then you just need to pass in here the name of the graph that you specified when you called the graph.load procedure. So hopefully that gave some guidance for that question.
Okay, what patterns or cipher commands would be best efficiently identify nodes with a higher betweenness in very large graphs?
So as Amy pointed out, there are, for the betweenness one in particular, we sorry, we need to look at the approximate betweener centrality. So the betweener centrality itself, so kind of just refreshing what Amy had said, it's an O of n squared cost algorithm. So it's looking at the shortest path between all pairs of nodes in the graph. There are approximation algorithms, so for instance, such as the R.A. Brandeis one, where you can reduce the amount of work that's done there. Now, it will obviously not be a completely accurate betweener centrality as what the betweener centrality algorithm does, but it will complete in a more reasonable amount of time. So there are two ways that you can do it. You can do it based on just randomly select nodes, and it will pick a random selection of relationships when it's working out like how many of these relationships should I be following when I'm computing my shortest paths, or you can specify the degree, and it will bias towards degrees who have a higher number of nodes. And with all of those, you can kind of fiddle. You can also, the last thing is you can set the maximum depth that it should look at on those shortest paths. So by default, it will look all the way down. So if two nodes are connected at depth 23, it'll compute all of those. It will compute that type of shortest path, and then it will be looking, well, okay, which node is sitting at the middle of that shortest path. But you can say, actually, I only want you to look at depth 5, and that's more than enough for my purposes. But in this case, the relationship is just in any way how you're connected. It doesn't. The relationship doesn't necessarily have the same meaning as it would need to with the PageRank algorithm.
Okay, I think we're out of time on this one. I'll respond to some things in the chat, but we'll go ahead and get rolling on the next session. So if you guys have anything else, otherwise, thanks.
Cool.
Thank you.
Thanks,
Bye.
everybody.